Cast is now starting. All attendees are in listen-only mode.
Good morning, ladies and gentlemen. Welcome to the second series of webinar brought to you by MEPN and MPC. My name is Tiong Hock, and I will be the moderator for this webinar. On behalf of the organizer, I would like to thank all of you for taking time to join this webinar. As at this morning, we received a total of 186 registered participants. We are very much encouraged by your overwhelming response. I was told that many more webinars and training programs will be rolled out by MEPN and MPC during the MCO period. First, let me do a short introduction on MEPN for the benefit of those who have not heard about us before this. MEPN, which stands for the Machinery and Equipment Productivity Nexus, was set up as one of the 9 productivity nexuses under the Malaysia Productive Blueprint introduced in May 2017. The main purpose of the productivity nexus is to drive the implementation of the initiative of each subsector as outlined in the blueprint in close partnership with the government. The Machinery and Engineering Industries Federation, or MEIF in short, has been tasked to champion MEPN on behalf of the machinery and equipment subsector. MEIF is a federation consisting of 8 association members and 1 university member with a combined membership in excess of 6,000. In 2017, the machinery and equipment subsector contributed 2.6% of the manufacturing sector's total added value and employ about 93,000 workers. In MEPN, I'm leading one of the working groups focusing on talent and manpower development. This webinar is one of our initiatives working in collaboration with MPC and Selangor Human Resource Development Center, targeting at business owners, managers, engineers of manufacturers, especially SMEs, who are keen to start their journey to IR 4.0. The title for today's webinar is Smart Factory, Data Generation to Predictive Maintenance. Our speaker for today is Dr. Chua Wen-Shyan. Before I pass the mic to him, let me do a short introduction with his biodata. Dr. Chua is currently the head of Malaysia's Smart Factory 4.0 under the Selangor Human Resource Development Center. He obtained his PhD in Control Systems Engineering and Bachelor of Engineering in Mechatronics Engineering from Monash University, Malaysia. His key areas of expertise lies mainly in the area of control and automation systems, fault detection and identification, and predictive maintenance strategies. He is actively involved in IET Control and Automation Technical Professional Network, and also is an active member of the Industry Advisory Panel of Monash University, Malaysia in the Mechatronics Engineering Department. At the Malaysia Smart Factory 4.0, Dr. Chua and his team are focused in delivering high-impact talent development program to accelerate the growth of local talents who would be the workforce in supporting the growth of Industry 4.0. Without further delay, I would like to now call upon Dr. Chua to deliver his paper. Dr. Chua, please.
All right. Very good morning, everybody. Thank you very much, Mr. Tiong, for the introduction for today's topic and also for myself. Thank you very much, MPC and MEPN, for the opportunity to share with everybody some of the topics on Industry 4.0 this morning, related more towards the smart factory and the predictive maintenance portion. And what I'll share with you as well today is also how SHRDC, Selangor Human Resource Development Center, we are an organization that supports the talent development of current workforce and talent pipeline within Malaysia. And of course, what are the initiatives at the Malaysian Smart Factory that actually helps to spearhead the Industry 4.0 talent development within Malaysia. So my name is Dr. Chua, and this morning I will share with you more on the topic with regards to Smart Factory, which relates to the data generation to predictive maintenance. So this morning, these are the table of contents that we will go through some of the topics this morning. We will share an overview on Industry 4.0. which some of you may or may not have gone through it before. We will talk about the smart factory, which is the integration of technologies related for digital transformation. And of course, how the smart factory concept of the integration and collaboration-based approach really supports the fast, flexible, and scalable integration from OT to IT. We'll discuss more about how data, when you generate a lot of data within your factory, how do you actually formulate equations of effectiveness to really look at the productivity of your production process, your equipment, machine health, and of course, really look at how data is really spearheading the evolution of maintenance strategies, which you will probably hear a lot of the term called predictive maintenance. And what I'll do is to share with you more in detail on how predictive maintenance really came about. And of course, to really discuss as well on some of the Industry 4.0 maturity levels, in which we actually break down even further for everybody in terms of the building blocks of technologies that we see on how you can really kickstart your journey. And of course, we will also share with you some of the concepts that we have in SHRDC that we support the industries, especially the SMEs, to kickstart and scale up at a very, very cost-effective rate. And of course, with that, I will also conclude the session today with some of the key takeaways for everybody to actually go through. So without further ado, let me start my presentation on Industry 4.0. So Industry Revolution 4.0, or IR 4.0 in short, we always see it as a journey towards digital transformation and productivity. So why do we really see it as a journey? If you look at the past, right, you look at Industry 1.0, it's all about mechanization, steam power, that's the generation where mechanization starts to happen. And of course, as we journey on, we go into Industry 2.0, which is more towards the mass production, the assembly line, and of course, looking at electrical energy to power up your plants. Now, when you go further into Industry 3.0, that's when automation starts to kick in, right? And of course, you have computers, you have electronics to really, really support your processes and really to provide you with really, really enhanced processes to increase your productivity and yield. Now, when it comes to Industry 4.0, it's not so much about automation anymore. It's more about connected systems, right? You look at cyber physical systems, you look at Internet of Things, you really look at the network, right? And all these machines or equipments come together and basically all are connected within one particular ecosystem, right, in your factory. And how this connectivity actually helps to bring up more data visualization and helps you to make better decisions. So that's what Industry 4.0 is really all about. Now, when we talk about smart factory, right, we really look into the integration of technologies of Industry 4.0, which is really used for digital transformation. So when we hear a lot about the 9 pillars or any pillars of technology, it's really more or less an integrated process. So when we look at a smart factory, we look into 2 levels of integration. One is the horizontal integration, where it's more towards the shop floor kind of integration that you see within the factory floor, where all the equipments and machines and the entire factory floor is all connected. Now, once you have that kind of integrated connection or network within the shop floor of your factory, then you go up vertical, where all your data that you collect and all the information that you have with regards to your production is really pushed up to the cloud or edge computing. We really look at AI or analytics. And of course, we look at cyber physical systems, and all these put together really enhances the digital continuity, right? Which is the diagonal integration approach, the digital continuity or synchronization, where you actually create what we call as a digital factory. So when you look at all this integration of technologies over here, what it actually tells you is that you are actually putting everything together into 3 main components, which is operational technology, information system technology, and the digital factory. So that's how the integration of technologies come together. So with that, we look at smart factory, which is we really think about when we look at integration of technologies, we really want to see how these technologies can be integrated through a fast, flexible, and scalable integration. We don't want technologies to be taking too long to actually integrate, and eventually you take a very long time to deploy, and that's when you actually lose time. Not only time, basically you invest a lot of cost, because time is basically cost. So when we look at smart factory, we think about it as a multi-vendor approach, right? Every machine needs to talk together, right? You have different brands, and that's okay, right? You have different brands of equipment coming together. You have different interfaces coming together, but all these equipments and interfaces need to talk to each other. And that's where you look at open communication protocols, where if you think about machines, right, it's similar concept as humans as well, right? When we want to communicate, there's always a common language that we always try to communicate with. Like, for example, English is a common language. So similar to machines, there will be a common language where each machine will have to talk to each other. If there is no common language, then of course you have a translator, right? So like, for example, we have Google Translate to translate English to a different language that we want to converse in. So same for machines, that actually happens as well. You have different communication protocols, and what you need to do is to integrate them such that each machine will talk to each other. Now, when you want to go fast and you want to go flexible and scalable, that's when the open collaboration concept approach comes in, right? You want to make sure that the technologies that you integrate together, they are powered by communities, they are reviewed thoroughly, and that's when you can actually utilize these kind of libraries available to actually spearhead your integration processes, right? You don't need to reinvent the wheel. And that's when the open collaboration approach really comes in to support what we call as rapid prototyping and development. You want to make sure that whatever you put together, it's really rapidly developed, okay? You don't want to take a slow pace to actually reach there. Instead of taking 3 months, you actually can achieve what you want to achieve in 1 month. And that is what we call rapid prototyping. And how this actually helps in overall is we reduce the time to deploy, right? You want technologies to be put together in a very fast pace, in a very easy approach to deploy. And that's how you actually achieve, right? When you look at this diagram over here, you actually achieve at the shop floor, you have data generation. You collect all the data from the shop floor with the communication protocols. You integrate it with a middleware, which is where your data aggregation comes in. And of course, what you want to achieve later on is you want to push this data into a database, right? You want to manage the data. And that's where your data management and storage comes in. And all these needs to be integrated more or less seamlessly with regards to the overall smart factory concept. So smart factory automation, or how we see it, is basically an integration of technologies, right? You don't just look at equipment and say that, okay, my machine needs to generate data, right? I want to make my machine generate data. We need to look at overall factory processes. What is actually important to you to have information, right? What you want is information. For example, if you look at this diagram, right? You talk about logistics where you have a truck and you have a personnel carrying boxes. You want to have traceability, right? So you need to put some level of sensors to actually manage that kind of traceability, right? You have to have wearables, you have RFID scanning, and then you think about, you want to look at inspection methods. So you look at computer vision for inspection, then you look at the robotics to actually support your operations, which are connected to an overall supply chain management. And of course, you look at industrial augmented reality, if that works for you, to really look at the product specifications through vision scanning. And all these are basically a particular operation where you want to integrate all these technologies and obtain information from every single level, right? You want to make sure that all this information are collected, aggregated, and managed throughout the entire smart factory automation system that you have. So that's how the integration of technologies come about. So once you have all this information, right, you get information from your machines, you get information from your shop floor, you get information from your logistics. What you really want to do is you want to find an equation of effectiveness, right? You want to understand if your current operation is really productive, it's really efficient, it's really effective, right? So one example of how we look at effectiveness for machines or production is basically the overall equipment effectiveness, right? Which is demonstrated as a very simple equation like this, right? You have availability, which is your A. A basically looks at your machine downtime, right? You want to make sure that your machine is up at a certain period of time. You want to track how in these 8 hours of your shift, how many times your machine is actually down, how long is your machine actually idle, which means you're waiting for parts, right? You want to know this information, and that's where you look at availability as an overall equation of effectiveness. You look at performance. So like for example, you buy a machine, right? There's a spec that says you can produce maybe 1,000 in 1 hour, but your actual production is only maybe 500 in 1 hour. Why? So that's where performance comes in. You need to look, what's your machine cycle time, right? You need to look, what is your machine idle time? What's your machine time or operation time actually moving? And that's where performance actually comes in. Now, and when you look at A and P, that's not just the overall variable of the equation, right? You want to produce good parts, good quality parts that meet your customer specifications. So then the next variable comes in, which is Q, right? You look at quality. You don't want to affect the quality. If you increase your performance, you may actually affect your quality. So all these are actually related to each other, and that's where we get, for example, an equation of effectiveness called OEE. So that's how you actually look at how data can give you that kind of information or traceability towards developing what we call as the equation of effectiveness. So then when we look at data, what else can data do to really help you in your daily operations, right? So when we look at the evolution of maintenance strategies, right, we want to go into strategies where it doesn't involve a lot of cost, okay? It doesn't involve sudden surprises or breakdowns, and that's where we look at predictive maintenance and prescriptive maintenance. So when you look at reactive kind of maintenance strategy, it's basically fixing your equipment when it breaks down completely. So that's the point when you see, oh, my machine is down and I need to fix it now, right? So that actually creates a lot of surprises. Okay, when your machine suddenly just breaks down, you have to quickly gather the spare parts, find the spare parts to actually fix it, right? And that takes up time. And so what some industries actually move towards to is that preventive maintenance, right? You have PM times. So at a particular month, this machine needs to go through a preventive maintenance scheduling, right? They need to schedule it, and they need to replace whatever parts within the line, clean up the line, fix in the right spare parts, and that are basically scheduled maintenance to prevent breakdowns, right? Now, when we look at predictive maintenance, that's another level altogether, right? You actually look at data-driven methods to actually predict when your machine is actually going to fail. And you actually are able to understand some of the signatures or behavior of the machines, the machine health diagnostic, to actually understand that your machine is going to break down or bound to break down. So that's something that we will discuss in more detail in a short while. Now, when we think about prescriptive maintenance, when we put AI in the picture, now that's something beyond predictive maintenance, where you have a set of known failures and known recommended strategies to overcome those failures. And when you match them together, that's when AI comes into place to really help you in your maintenance strategy. So when a personnel comes and maintain a machine, they know what to do at a very, very fast pace, right? So that's basically what the evolution of maintenance strategies that we share here is all talking about. Now, when we look at the journey towards predictive maintenance, we really need to ask ourselves 3 questions. What we really intend to achieve, right? Do you just want to know whether your machine is operating normally? Or do you want to know why your machine is not behaving properly? Or do you really want to know how long do I have before my machine stops running, right? So when you want to know whether your machine works normally or not, that's really more of anomaly or fault detection, right? You really want to know whether there is an anomaly in the system that will affect your machine to be at a stage where it is not healthy anymore. And when it's not healthy, it will start to slowly degrade and start to break down. So do you want to detect that anomaly at a very fast pace, right? And do you just want to know that, oh, I have a problem and therefore I will stop the machine? Or do you want to then go deeper into why my machine is not behaving properly? So that's when predictive analytics comes in, right? You are able to identify what is the signature of the machine that is telling you that it's not behaving properly. For example, Is it a bearing having a problem, or is it there's some problems with the sensor, or is there some other problems that leakage in the system that we don't know? So that's where predictive analytics comes in. Now, how long more do I have before my machine stops running? So that is basically what we look at is in a term called remaining useful life, which is slightly beyond predictive maintenance, but basically with the analytics information that you have, you're actually able to predict the rate of degradation, and eventually you are able to understand how long more you have before your machine will stop running. And that's basically the overall picture of the journey towards predictive maintenance. And basically strategies of predictive maintenance really revolve around a very similar concept like this, right? What we look at basically is we look at data, right? You really want to do data. You really need data to actually understand the predictive maintenance strategy. It's a data-driven strategy. So you look at real-time data acquisition and processing, where you take useful data, and I must emphasize the word useful, because a lot of people, they have a lot of data, but what happens is that most of the data is not useful to actually do a predictive maintenance strategy, right? It's not useful data. And what we want to emphasize is collection of useful data, and you store it, and you pre-process the data, okay? And you identify characteristics. So in layman terms is that you have a lot of information, right, about a person. And what you really require is useful information of a person to actually identify their behavior, their characteristics, or their features that really signify what is that person all about. And from there, basically you develop a model, right? With all this information, you develop a model. So it's basically you are trying to have a first impression, right, of a person. You develop a model, and then you train the model. You actually understand better, right, what the entire model is trying to tell you. And once you're ready, basically you deploy, you integrate into your system, and you have to validate again. It's a continuous loop. So it's not just as simple as, okay, I want to have predictive maintenance. I'm going to put a tool there that will tell me every information I know about the machine. That's not as straightforward, because a lot of times there's a lot of data being involved. And of course, there's a lot of features and characteristics that you need to identify, because processes in a factory are very, very different. So it's like you have a bank and database, a universal bank or database of data where you can actually use to do all your feature characteristics. And that's where your data storage is very, very important to identify your historian data and therefore develop a better predictive maintenance strategy. So very simply put together, how this whole predictive maintenance really is explained is basically, you think about it as a machine translator, right? Like what I mentioned before, machines can talk to you. All you need to know is they need to tell you in a language which you understand, right? So think about it like Google Translate, right? You try to put in English, and then you get probably Spanish or Chinese or any other languages that you want to hear. Machines are the same, right? Instead of alphabetical languages, what it provides you is basically values, right? Data. So if you look at signal over here, for example, this is a signal of a motor, okay? And what it does is that it needs to detect, your algorithm needs to detect this, okay? It needs to scan through. And what it does is it will tell you, for example, that I am not well, right? The machine is not operating properly, right? So using these kind of data signatures, you're able to predict or detect whether your machine is operating properly or not. So that's basically what we call as anomaly detection. So based on the data, you're able to tell that the machine is not working, right? And when you want to deep dive further, right, basically the same data set that you have, you want to scan it further to really understand, is there any underlying problems that are not sure, right? You want to diagnose the machine. Why is it not well, right? So you have to put in other algorithms in place to actually look deeper, right? Based on the historical data that, okay, I'm not well, and why I'm not well is one of my parts are loose, right? And then you want to drill down further into how long do I have before you will shut down, right? So that's basically looking at the overall strategy of anomaly detection, right? Predictive maintenance and remaining useful life. So your data, basically whatever data that you collect, are able to inform you of this information, right, through time. And once you're actually able to achieve this, so basically you are able to achieve predictive maintenance and able to understand the remaining useful life strategies, and therefore that will give you a lot of insight towards your current production systems on whether or not your systems are operating well, they are in a good shape, and you are able to increase the useful life of machines. So if we go into what we call as the P to F curve, this is a very simple curve that explains really in depth on when we look at the health condition of the machine, right? And you look at the time, over time, right? When you buy a machine, basically you buy a machine that's healthy, right? You want to buy a new machine, you have the machine is able to run for many cycles, but along the way through the cycles, over time you will see that the machine will start to degrade, right? So we have 2 points, right, to think about. One is potential failure and one is functional failure, right? Potential failure is the point where the equipment starts to fail. You start to hear noises, you start to hear something is not right about this machine, but that's based on intuition, right? You know that something is not right, and before you know it, eventually the machine starts to fail, right? And that's when you start to perform reactive maintenance because you need to fix the machine, right? Or basically in between here, what you do is preventive maintenance to sort of bring back the health of the machine at the particular point before the potential failure starts to happen. But what affects this is that your cost will actually increase, and of course when you stop the machine, you implement downtimes that will actually affect the overall flow and the overall scheduling and cost of your particular production. So what industries usually do is that they can apply condition monitoring methods over here. We actually look at the condition of the equipment to determine the rate of degradation. So how fast, right, from potential failure to functional failure, what is that interval? And can you actually maximize that interval, make it longer? Or is your strategy actually making it smaller? That means from potential failure to functional failure is actually a fast degradation. So what predictive maintenance actually does, right, is that it brings you to a point before potential failure and is in the middle of a point where it is the actual start of the failure. So you want to be able to predict when the fault actually happens or the anomaly actually happens somewhere over here before it reaches to a point where your machines need to break down and you have a lot of quality issues, you have a lot of efficiency issues. When you look at OEE, your OEE may be affected somewhere here, right? So that brings down your effectiveness, right? And when you look at the overall quality part of it, maybe it increases your failure rate somewhere here. So you don't want that to happen, and you want to be able to predict when this actually happens in overall. So if you look at this diagram, this is actually a very straightforward diagram on how, the more descriptive of how your actual start of failure actually looks like, your functional failure actually looks like, and your anomaly detection and estimation procedures, which will actually help you to predict the actual failure, right? So let's look at these 2 diagrams. You have motor position, which is actually your motor running, right? It's running at a standard phase, right? And then what happened here is that there is a big spike, right? And this actually happens because there is a sudden surge of anomaly within the particular system, right? Which we do not know, right? There could be a sudden sensor problem, there could be a sudden bearing problem or actuator problem, which we need to find out. So if you put in your anomaly detection and estimation strategies for predictive maintenance, what happens in this second graph over here is you could actually see that there is a gradual increase of degradation or signals from your sensors that actually show that there is a problem, right? And if you put in the right strategies, you're actually able to estimate this particular signal. And before this functional failure happens, you're actually able to take the necessary steps over here to actually mitigate this from happening, right? So if you look at this here, you actually see some form of degradation, right? A very, very minimal part of degradation, but you are not able to see whether it's really a machine problem or maybe it's just your data collection problem. But if you put in the right strategies, you're not getting false positives, right? You're actually able to see where your machine starts to degrade, and then you can put in the right methods to actually cut short, that potential failure cost, the functional failure cost, and you're actually able to detect it early, hence reduce the cost due to unexpected failures. So things like this are unexpected, and if this actually happens, it may cause catastrophic kind of events, right? It may actually hurt someone in your operations. It may actually hurt your machine even more if it's a chain effect. So what we want to do is really to predict it early so that it doesn't give a chain effect to all your other machines in the same line to actually break down everything, and then you cannot run production. So that's what predictive maintenance is all about. Now, if you look at this is all good. It's basically very looks like a situation which is a very ideal case that we want to achieve, right? We want to maximize the P to F interval, and that's what we really want to achieve, in terms of early detection using predictive maintenance strategies. But the key challenge now, when industries talk to me about, I want to have my shop floor to have AI, right? I want my shop floor to have predictive maintenance. I want to run a lot of analytics to my system, right? So the first key question that I would usually ask is, do you have data, right? Because all this analytics strategy requires one key component, which is data, all right? So some of the industries will share that, yes, I collect data, right? I am able to generate data. My machine is providing me with information. So next question would be, what kind of information are you getting? Is it reflecting your daily operation? Is it able to predict situations like this? All right. So that will be one question. Now, the next question to ask is, we talk about data storage, right? So along the way, 3 to 6 months time, are you collecting all this information of data to actually analyze and build your predictive maintenance model? So that is a very important question, because a lot of times is that some of them will say that I have data. Today I collect it for 1 week, right? Next week, my data is not collected because the machine is down. Following week, I managed to get it up, but my sampling rate of the data is not correct. So you have inconsistency in your data collection, and that actually affects the overall quality of your predictive maintenance strategy. You're not teaching, or you're not learning at the right pace. It's like, for example, you're teaching somebody what is an apple, right? And you always give an apple every day until the person knows that, okay, this is an apple. But the moment you give him an orange, right? The only thing that the person will tell you is that this is not an apple, right? So you need to teach back that this is actually an orange, okay? And it is not an apple. So that basically is all data driven, and machines learn in that kind of manner, right? You need to give them enough data for them to identify what is different and what is a feature or what is a characteristic of an apple or orange for it to understand that, okay, this is definitely not an apple and this is an orange, right? So that's what you intend to achieve in the overall predictive maintenance strategy. And that's really boils down to the key component, which is data generation. And with that, let me bring you closer to how we want to achieve effective and accurate predictive maintenance. So we really look at the whole Industry 4.0 maturity levels, right? We actually break it down for you even further. So you have the pillar concept, you have the integration-based concept, which is broken down into 3. Now we go deeper, right, into really looking at the maturity levels of each industry, okay, in terms of building blocks of technology. So we break it down into 5 levels, right? Level 1 is data generation, right? If your machine is producing data, then that's very, very good. If not, you're still at level 1. Now, next, level 2, you look at visualization. So when you collect a lot of data, you want to basically make sense of the data, and you want to visualize it such that you want to see features along the way. And that's where data visualization comes about. You want to see how this data plotted together will actually look like. Now, with generation of data visualization comes the important concept of storage, right? You have many, many cycles of machines running per day, and you don't want to just collect for 1 week and then discard it and then that's it, right? You want to look at the overall machine health throughout a certain period of time. As you look at the P to F curve just now, right? You have a very straight line of machine health, and then it starts to degrade. So it's not that interval of time is not just like 2 months. it could actually go up to 8 months, or even further into 12 months, depending on how many cycles your machine actually runs. So it's not just a 1 week data collection kind of method. It's throughout a whole period of time if you want to really achieve effective predictive maintenance strategy. So that's when data storage comes about, right? You need to be able to store those kind of information in your on-premise servers or even in your cloud servers, and that's something that you need to think about. Now, when you have a lot of data put together, you have a lot of information put together, the next thing you need to do is you need to formulate those data. You want to make sense of what the data is actually telling you, right? It's all in pieces now. And what you want to do is you want to put them together to actually give you an information or the right information to tell you whether your machine is healthy, not healthy, your machine is productive, not productive, effective, not effective. You want to know that kind of information. So that kind of information is where you get in terms of data formulation, right? You need to formulate your data, and that's where you can identify certain key characteristics of your system. And before running analytics, you are actually able to implement control mechanisms to actually detect anomalies. For example, you can look at OEE, which looks at the overall equipment effectiveness. If your OEE is like 50%, then you need to find out which part is giving you the low percentage. Is it your availability, which your machine always goes down in 1 hour, or is it your performance, or is it really your quality? So that's the 3 key areas that you can actually identify where the problem comes about. And all these are basically data driven. You know, there's a lot of transparency, there's a lot of information that you can have to understand your process a bit better. So once you actually have all these in place, you have a lot of data, your people in your factory have the domain expertise, right, of your machines, they understand it well. That's when data analytics come about. So that's when you reach a level 5, right? So all this data that you have, your historian data, you put together, you create models of your operations, and that's where you are able to achieve the right analytics strategy to actually implement to your system to identify what are the key failures, and of course achieve predictive maintenance in the long run. So data generation, you know, put it simply, like when you see this diagram over here, right? Basically, you are looking at one of the dashboards that are there in our center, in one of our kits. Right. So what this dashboard actually show you is that it actually sees the machine status monitoring, which is tower lights. It looks at temperature monitoring, power consumption monitoring, which is important if you have heating elements. Right? You want to know whether there's a problem with your heating elements. You want to know whether your powers are being generated well. If there's a surge, you need to know. And of course, these kind of dashboards that you can see here, they also have alert triggers and notifications and mobile application and alerts. So this is actually level 1. You are generating data, right, into your system, right? You want to see how your data is being collected, right? And now it's actually being visualized through some gauges and some charts. So this is basically what you need to think about in terms of data generation. And data generation can happen in 2 ways. One is that if you have a PLC in your factory, you can collect your data from your PLC, provided you have control over that PLC, right? But what if you don't have control over your PLCs? You want to still collect some data, some information, and that's where you need to look at different hardware that are able to collect data from what we call as legacy machines.